Hi all! What I'm going to show you is a custom sound monitor solution that I designed and built from the ground up. It involves some off-the-shelf hardware components as well as some custom software that I wrote. So I'll show you the hardware, the software, and then how I put it together. Now the purpose of creating this little device was actually to monitor aircraft noise because I happen to live very close to an airport. And you'll see that as we take a tour of the application. Without further ado, let's have a look. So for the hardware, I have this cheap little Raspberry Pi 3B, well I guess they're not so cheap anymore, in a case that I bought from Micro Center, of course. And here we have a little microphone which I also bought from Micro Center. Sorry it didn't focus better. And then I have this little sound level meter. It was about $40, it is USB based. I bought it from overseas and it does a nice job of measuring the sound level in the environment. So at this point, we'll go ahead and hook everything together. So the sound meter hooks in via USB and the microphone via USB as well. And the only other thing we have to do is hook in power and we're all set. And we'll see the sound meter spring to life with the readout on the display. I'll go ahead and give you a close-up of that as well here in just a second. There you can see it, the sound level bouncing around all over the place. Looking at the application interface, it's not all that sophisticated, but it does get the job done. First, we have sound data statistics, which includes things like the device name, microphone status, when the application was started, as well as the current time, the current sound level as provided by the sensor, the average sound level over the past 60 seconds, as well as the number of samples recorded since application start and total. And we also indicate the CPU temperature of the Raspberry Pi. The next section is logging. We can actually clear any existing logs that are there. Logs are handy for telling you what sorts of things are going on in the application. We can also grab an audio sample, which allows us to grab 10 seconds worth of audio. The system is forever recording, so we grabbed 5 seconds of audio in the past and 5 seconds of audio starting from when we press the record button. Let's take a listen as to what one of the samples sounds like. In the next part of the application, I have a little graph that tells us the different sound levels that have been recorded. I only log recordings over 65 decibels for 3 or more seconds. And next we have a readout of complaint counts by month. You can see that there are a variety of aircraft that fly over my house with a reading of 65 decibels for more than 3 seconds. Next we have the list of reported complaints. And these are complaints that I can just basically save in a database. To date, I've submitted just a few, and I have a few that I need to submit that have been recorded, and currently there are none that are being processed, if you will. I can go ahead and export what you see here to a CSV file and open that up if I wanted to go ahead and track things a little bit better. And if I were to expand the number of complaints that we see right now, there would be more results in the CSV file, but for now we just get 10. I also have a button for auto-submitting the complaints to a database. We'll go ahead and go through that, and you can hear a couple of samples that are out there. We can also pick a clip in the list and play it if we want to hear it. And looking over to the right, you can see the status of submission. And we can also change the number of clips that we view at any given time. I have bumped this up to 20. And from there, we can scroll through the various pages. So now we can see that we have just a few pages of complaints. There are also a variety of reporting interfaces, and we can turn these on or off. The first one here is a database record report, and we will talk about these more in detail later. But I can enable or disable that, and the reports will be sent to the database or not, as well as email and system health, web complaints, and web sockets. We'll talk more about those in a bit. And here we have a graph where I graph individual sound samples. Anything over 65 decibels will appear on this graph, and these are sound recordings over the past 12 hours. Next, I'm going to show you a report coming in real time. Keep an eye on the red arrow, and you'll see a new line appear with no sample for the clip. but a clip will appear in a couple of seconds. I always record 5 seconds in the past, and then I start recording as soon as I detect the sound event. And we'll play this for you in just a second. This is me yelling at the sound Pi and testing it so that it generates a new report. So there you go, and that's how it works. Let's take a few minutes and have a closer look at the architecture of this system. So over on the left we have a microphone and sound meter, which we've already seen. In the center we have the software that's hosted by the Raspberry Pi, and we're going to go over these components in some degree of detail. And on the right we have a web browser where we saw the user interface just a few minutes ago. All sound samples and reports are stored in a Maria database. So let's go ahead and have a look at the database architecture. As you can see here, the database architecture is actually pretty simplistic. First, we have a table with sound readings in it. Each sound reading has an ID, a sound level, and a current date timestamp. Sound readings are taken in half-second intervals. So basically, for an hour, we will have 120 sound readings. Another table we have is the complaints table, and we'll have a look at some of the columns in more detail here. The average interval sound is the sound level that has been in the environment over the past 60 seconds. And the complaint receipt is a unique identifier I store for every single complaint. Additionally, the sound samples are stored in the database. These are stored as MP3 files, as binary objects, to keep everything nice and together. Otherwise, I'd have thousands and thousands of sound samples scattered across the disk. I'd rather store them in the database. Other columns you'll see in the table include the ID, the sound level, the current date of the complaint, and the status, which indicates whether the report has been submitted or not. Additionally, each column that you see in bold, so that would be the sound level, current date timestamp, and status, are indexed, and that makes it easy for us to gather statistics on those particular columns. We also store some metadata in the database, and the metadata table currently only has one element, which is total samples. And this value ends up being a rather large value since the system has been running for quite some time. What I found is, over time, the system got slower and slower on startup. It was counting up the total samples in the database on startup. Since things were getting slower, what I decided to do was, rather than count the samples on startup, was to save off the total sample values in database metadata. And the way that we update this is, every time a new sample is put in the database, this trigger below fires and increments the total samples that you see in the metadata table above. So basically, rather than asking the database to count every single element, we can just go ahead and grab this one number and display the total samples recorded. Next, let's have a look at the Sound Monitor Client, which is based upon the Dropwizard framework and is, for all intents and purposes, a Java application. Here you can see a glimpse of the source code where the Dropwizard application launches, and you can see there are a variety of Java files that correspond with this application. The Sound Monitor Client has a variety of sensor components. We'll go ahead and talk about those now. First, on the left, you see the Sound Meter Interface. And the Sound Meter Interface is custom code that I wrote by reverse engineering how the sound monitor works. And I found it best to write this in the C language as opposed to Java, so we have this JNI class here which interfaces with some C code, and this is essentially the driver that I wrote for purposes of getting information out of that sound level meter device. Pretty cool. Next we have the Sound Report Processor, and for every sample that comes from the meter, it's going to go into the Sound Report Processor, which is then going to take those reports and put them onto a queue. Additionally, as I noted earlier, the microphone is actually always recording and keeping the last 5 seconds of audio in the past. So we need to be able to blend those reports that come in from the processor with the audio output from the microphone. As such, both of these elements feed into the report element you see over on the far right. And reports do come in a variety of shapes and sizes, more on that in a minute. And each report can have its own criteria for generation as well. Perhaps we only trigger a report based upon a certain sound level or duration, and this is fully configurable. So the Sound Monitor client also has some server management components, and you can see those here. There are components for managing web complaint reports, as well as statistics and log management, and we saw some of that earlier. Both of these types of interfaces are REST interfaces which happen on request, essentially. So anytime somebody wants to know about this particular interface, it can make a call to it and get the information it needs. We also have a variety of WebSockets, and these WebSockets are for giving real-time updates to the application. The WebSockets include providing statistics and reports, as well as providing web complaints and logs. For the statistics and reports, when we saw that new report come in, that came in via a WebSocket. And we also saw the numbers changing at the top as the sound level changed. That also came in via statistics. Next, let's have a look at the variety of Sound Monitor client reports. So first and foremost and most critical is the database record report for recording every sound sample. We also have system health reports, which record things like the microphone health as well as the temperature of the Raspberry Pi CPU. We also have the concept of a web complaint report. And we saw this earlier when we saw this screen with submit and delete. Those are web complaints. We also have the concept of a WebSocket report. And as we saw earlier, we had all of these nice statistics that we're streaming in. That came from the WebSocket report. And we also have the concept of an email report, which allows me to send an email somewhere whenever certain criteria are met. Again, all criteria are user configurable. We also have the ability to submit a network caller ID report, which is a system that I actually helped develop. I wrote the application and desktop application for this project that you see here. And it's basically a socket server that allows for aggregation of information related to calls, texts, or other types of information. In this case, noise complaint reports. And speaking of report customization, here's all the report criteria that allows you to customize a report. We have a concept of hysteresis, max allowable historical average over time, the minimum delta between current sample and historical average, and whether or not a report is enabled or disabled by default. I won't go into the whole algorithmic piece of it here, but suffice to say, the concept is give the flexibility to submit a good report without submitting a false alarm. Next, let's talk about the Sound Monitor server, which is also a Dropwizard application. And I do realize my naming convention is a little strange. The server is basically what serves requests to the end user, and the client interfaces with the sensors as we saw. So let's have a look at the server. Similar to the client, the server is a Dropwizard Java application. I've opened up the main class here, which gets everything up and running. We have initialize and run commands, and all of the good magic that has to happen to get things rolling, as you can see. And there are a variety of class files associated with this particular application as well. We also have code in React.js for purposes of serving that front end. It's not a fancy front end, but it gets the job done, and I'm not a front end developer by trade, so I'm somewhat proud of myself for putting it together. Let's have a look at the individual Sound Monitor server components now. And as noted, this was written in React.js, and there is an audio player, a web complaints component, a stats and reports component, and a component for the three lovely graphs that we did see. And the server also has some read-only data access for purposes of receiving graph data retrieval, sound clip retrieval, and web complaint data retrieval. I didn't want to burden the client with this, so I put this on the server side. The client focuses more on sensor and data aggregation, whereas the server can focus more on any sort of access it needs for display purposes. And that's a tour of my aircraft sound monitor. In all cases, I hope you enjoyed the video. Thanks for watching, and we look forward to seeing you next time. Bye for now.